In this video, we're going to look at some of the reactions of carbohydrates that have kind of led us in terms of really deducing the structure of them, and we'll kind of see how that plays out later on in the video. So the first one that we're actually going to talk about is what we call MUTA rotation. And what does this mean? Well, let's say I start with D-glucose, right? So here is the Hayworth projection of D-glucose. And hopefully you can tell I chose a particular anomer of D-glucose, and that anomer is the beta anomer. And if I have a solution of pure beta D-glucose, and I look at the specific rotation of beta D-glucose, I get a rotation of plus 18.7 degrees. Now, keep in mind though that any pyranose structure, any ring structure of a sugar, still exists in equilibrium with its free aldose. In other words, there is an equilibrium established between the hemiacetal and the aldehyde. And that aldehyde certainly exists in trace amounts. But if we think about that aldehyde reforming the hemiacetal, we can get more beta anomer, but we could also get we could get some of the alpha anomer as well. So here I've drawn the alpha anomer. Now, if I start with an optically pure solution of the alpha anomer, I see that it has a specific rotation of plus 112 degrees. So again, understanding that there is an equilibrium that is going to be established between the beta anomer and the alpha anomer, and a trace amount of the open-chained aldohexose, we see that if we place either one of these in water, what happens? Well, if I take pure beta anomer or pure alpha anomer and I place it in water, then an equilibrium mixture ensues, right? They equilibrate with one another, and I get roughly 64% beta anomer and 36% alpha anomer all the time. So that is the ratio that is established at equilibrium. And that particular ratio has its own specific rotation, obviously, of plus 52.7. So this is what we refer to as MUTA rotation, that regardless of which one I start with, if I place them in water, I get this equilibrium established that sets up this 64%, 36% mixture of the two anomers of one another. So that's our first reaction, and of course it's not, I mean, it certainly is a reaction, but it's an equilibrium process that's taking place. Now the second reaction is also a type of equilibrium, and it is called epimerisation. And so what happens in epimerisation is you form epimers of one another. Now this isn't under neutral conditions, it's actually under basic conditions. So it's important to understand the particular types of conditions. So if I put a sugar in basic conditions, what happens is it actually equilibrates with other types of sugars, not just anomers of one another. So for example, here I'm going to draw the chair conformation of D-glucose. It could be either the beta anomer or the alpha anomer. So notice I'm using that squiggly line. So this is D-glucose or D-glucopyranose if you're thinking about the pyranose ring. And I'm going to place this in an aqueous solution of calcium hydroxide. So certainly calcium hydroxide is a base, so we're using basic conditions. What I find happens is that I get a conversion of some of the D-glucose into an epimer. So remember, an epimer is a sugar in which one of the stereogenic centers is changed. And so you see that C2 carbon the OH has gone from an equatorial to an axial. So we've changed the stereochemistry of that one particular stereogenic carbon. And if a good little practice would be to figure out what the name of this was, if you could actually draw the Fisher projection of this, and I'd certainly suggest you maybe pause the video and see if you can do that real quick. And if you did, you'd find that this is D-mannose. Okay, so now there's another um, sugar that actually can equilibrate with D-glucose and D-mannose. Again, in this basic conditions, right? So keep in mind we're just in these basic conditions, and another sugar develops, and it has this particular structure. So notice this is not an aldohexose. This is a ketose, and this particular ketose happens to be D-fructose. And so at equilibrium, what we see is a mixture of 63.4% D-glucose, 2.4% D-mannose, and 30.9% D-fructose at equilibrium. So these things are, we're losing roughly a third of the D-glucose to other sugars at equilibrium. We call this reaction the Lowry-de Bruyn Alberta van Eckenstein reaction. The Lowry-de Bruyn Alberta van Eckenstein reaction, named by two chemists that actually discovered this type of phenomenon. Now, obviously, when we see something like this, we should be asking ourselves, how is this actually happening? And so in order to do that, we have to look at the mechanism. And we find that pretty much the mechanism is relatively straightforward if we stop and consider the particular structures of D-glucose. So we know that D-glucose mainly exists as its pyranose ring. There's some of its furanose ring as well, but there are also traces of its open-chained aldohexose structure, right, which we draw the Fisher projection of. So here I have the open chain of D-glucose, and what do I notice? Well, I notice that there's an aldehyde, right? And I learned already that aldehydes have acidic alpha hydrogens. And of course, D-glucose has an alpha hydrogen, and it is acidic. And so if I react this with hydroxide, I can actually deprotonate that alpha hydrogen, which is right there. And of course, what am I going to form? I'm going to form an enolate. So let's see if we can draw the enolate. We're going to form a carbon double bond between C1 and C2, and then the oxygen of our carbonyl is going to have a negative charge. And so here's the structure of that. So notice C1 now is has a carbon-oxygen single bond. Oxygen has a negative charge to it. I have a double bond there, and then C2 has only an OH off of it, and then of course the rest of the chain that is associated with it. So what can I do? Well, again, this is an equilibrium process, and of course I could simply reprotonate that, right, where the electrons from oxygen swing down and form a double bond, and then the enolate carbon removes a proton off of the water. So I end up, notice C2 in its enolate form has lost stereochemistry, right? It's no longer, it's an achiral carbon. So when I place that hydrogen back on, I can get back D-glucose, or the hydrogen can go to the other side, right? If I protonate the other side of it, what do I get? Well, I get the hydrogen now on the right side, and the OH is going to be on the left, and reforming the aldehyde. And so, and of course, obviously, this can then be deprotonated, right? And I can go backwards. But this particular structure is D-mannose. So now I know where the D-mannose is coming from. And of course, D-mannose is then going to cyclize and form a hemiacetal. And so that should make sense to us that, that's where we're getting the D-mannose. Obviously not a whole lot of D-mannose, but certainly enough D-mannose that we can isolate, right? And of course, that reaction is in equilibrium with the free enolate, right? The straight chain enolate, which is in equilibrium with D-glucose. Okay, so that explains the formation of mannose. But how do you explain the formation of D-fructose? So what we're going to do is we're going to re-examine the enolate, and I'm simply going to, on the next page, I'm going to redraw this enolate that's in the middle here. So I'm simply redrawing the enolate, right? And when I think about protonation, we saw that you can certainly protonate that alpha carbon, and of course the hydrogen can go on the left or it could go on the right, and so you get the two epimers of one another. But the other possibility is that instead of protonating the alpha carbon, you actually protonate the oxygen that has the negative charge. And so that's exactly what we're going to do. We're going to protonate the oxygen instead of protonating the carbon, and we get this. Now, what is this called? Well, this is called a double enol, right? Because I have OH groups on both of the carbons of that double bond. So what can happen? Well, in a double enol, I can deprotonate the other OH group, right? And then electrons from that oxygen, which would now have a negative charge, can form a carbonyl, and I would form an enolate on that carbon. And then in water, I can actually form a different type of carbonyl, and that carbonyl would be on C2. And this is where we actually can form D-fructose. And so you can see the mechanism is simply an equilibrium of enols and enolates, right? The next reaction that we're going to talk about is a reaction that we've already seen before, and that's called reduction. So we have seen that the open form of sugars with the aldehyde can react even if there's trace amounts. That trace amount can react with sodium borohydride and reduce the aldehyde to an alcohol. So for simplicity's sake, I'm not going to use D-glucose. I'm going to use something a little bit smaller chain. So we'll start with a carbohydrate like this. Now, you should know the name of this. It is aldotetrose. It is D-erythrose, right? So make sure that you remember the name of D-erythrose. And of course, if I take D-erythrose, I see that it has an aldehyde right there on the top. And if I react that with sodium borohydride in water, I can reduce D-erythrose into this, right? So I reduce the aldehyde into an alcohol. And now you see that basically every single alcohol, all four carbons contain an alcohol functional group. So if I were to name this, I would name this 1, 2, 3, 4 butane tetraol. Now, the interesting thing about this particular product is that for most carbohydrates, there is asymmetry, right? At the top there's an aldehyde, at the bottom there's an alcohol. When I reduce the aldehyde to an alcohol functional group, I can see now there is a plane of symmetry in this particular product, and therefore this product is a meso compound. And so this is one of the tests in order to determine the stereochemistry of sugars, is to reduce them and say, okay, I'm going to add a functional group that mirrors the functional group at the bottom, right? And therefore, I can now see what the orientation of the other stereogenic centers is. So that's one way that we can start to classify carbohydrates. The next reaction that we're going to take a look at is oxidation. So we can, and we've already seen that the aldehyde can be selectively oxidized using bromine and water, right? So this is this was one of the processes that we used in the rough degradation. It was a part of that particular process. So if you simply use bromine and water, what you get are called aldonic acids. So we're going from aldohexoses or aldopentoses, or however long the chain is, aldoses, to aldonic acids. So aldoses to aldonic acids. And again, if I use this particular structure, which you should be very well acquainted with, right? D-glucose. Get used to drawing all those, all those Fisher projections of D-glucose. Hopefully, by the end of the chapter, you will just it will be second nature for you to draw D-glucose in both the Fisher projection and the Hayworth projection, and in the chair conformations. Right. So if I take this structure and treat it with bromine and water, what happens is the aldehyde selectively gets oxidized. And all of the other alcohols remain intact, essentially. So all I'm doing is converting the aldehyde into a carboxylic acid. And this is what I get here. So notice the aldehyde at the top is now a carboxylic acid, but all of the other alcohols remain unoxidized. And this is what we refer to as D-gluconic acid, right? So the aldonic acid, this is gluconic acid, where you have a carboxylic acid at the top and the rest of the sugar essentially remains the same. So there are other stronger oxidizing agents, and one in particular is a mixture of sodium nitrite with nitric acid. So you get, it's actually a combination of nitrous acid and nitric acid. And when you use this combination of oxidizing agent, you get what are called aldaric acids. Or aldaric acids, however you want to pronounce them. So again, I'm going to start with my Fisher projection of the open chain of D-glucose, right? And I'm going to treat this with sodium nitrite in nitric acid. Notice it's at 0 degrees. It's a very exothermic reaction. And what I end up getting is I oxidize both the aldehyde at the top and the primary alcohol at the bottom. So now I have two carboxylic acid groups, one at the top and one at the bottom. And this is what we refer to as D-glucaric or glucaric acid. I typically say glucaric acid, but I think I've heard other people say glucaric acid. Now again, notice both groups are the same substituent, and so you have to think about optical activity of the resulting sugar. So for the glucaric acid, you see that it's still asymmetrical, and so this would still be optically active in terms of its optical activity. Okay?